If you step outside tonight and look up at the sky, nothing about it suggests urgency. Nothing hints that anything enormous is already in motion, because the stars appear fixed, calm, almost permanent. Yet right now, an entire galaxy is moving toward you, not metaphorically, not slowly in some abstract cosmological sense, but physically, gravitationally, relentlessly, and that galaxy is Andromeda, a vast spiral containing roughly 1 trillion stars, drifting through space directly toward the Milky Way, closing a distance of about 5 million light years at a speed of roughly 110 kilometers per second, which sounds gentle by astronomical standards, but becomes overwhelming when you realize that nothing will stop it. Not the expansion of space in our local region, not any orbital deflection, not any cosmic accident, because the gravitational pull between these two giant systems has already locked in the outcome billions of years in advance. You might imagine a violent collision, galaxies smashing together like cars on a highway, stars exploding everywhere, debris filling the sky. But that intuition comes from thinking of galaxies as dense objects, when in reality they are mostly empty space, enormous islands of stars separated by distances so vast that even when the galaxies interpenetrate, individual stars almost never collide. Meaning that if you somehow stood on Earth during the earliest stages of this encounter, you would not see an explosion or feel a shock wave. You would instead watch something far stranger, the slow reshaping of the sky itself, a transformation measured not in seconds or years, but in millions of years, subtle enough that no single generation would perceive the full change, yet dramatic enough that the night sky would eventually become unrecognizable. Today, Andromeda appears as a faint smudge, barely visible to the naked eye under dark skies, a small elongated blur in the constellation that shares its name. But that smudge is actually the bright core of an enormous structure, far larger than the full moon in apparent size. And as the galaxy approaches, that faint blur will gradually expand, first becoming a brighter patch, then a stretched glow, then a sprawling luminous form with visible structure, spiral arms faintly etched across the darkness, star-forming regions glowing blue, dust lanes cutting through the light. The entire galaxy slowly growing year after year, not fast enough to notice overnight, but unmistakable over centuries, and eventually impossible to ignore. This is not speculation invented for dramatic effect. Astronomers have measured Andromeda's motion directly using Doppler shift, analyzing the light from its stars, and finding that it is blue shifted, meaning the galaxy is moving toward us. And from that shift, they calculate the velocity and project forward, arriving at a time scale of roughly 4 billion years before the first major interaction begins, which sounds unimaginably distant. Yet on cosmic scales, it is practically imminent, closer in time than the formation of Earth is in the past, closer than the time it took multicellular life to evolve. And during all that time, gravity continues doing the same simple thing it has always done, pulling mass toward mass, gradually tightening the trajectory until the encounter becomes unavoidable. The important point is that nothing about this event is sudden. It unfolds with a patience that only the universe can sustain. Two giant spiral galaxies drifting closer over billions of years, their dark matter halos already beginning to overlap long before the visible stars do. Their outer regions feeling the first weak tidal forces, their shapes subtly stretching, the first hints of distortion appearing far earlier than any dramatic overlap. And throughout all of this, the solar system continues orbiting quietly within the Milky Way, unaware, unaffected in any immediate sense. carried along as one tiny passenger inside a structure that is itself moving toward transformation. From a human perspective, the sky feels timeless, but in reality it is just a snapshot taken in the middle of a long motion, and the stillness you see above you is only temporary. A pause in a much larger gravitational dance that has already begun, whether anyone is here to witness its conclusion or not. To understand what it actually means for Andromeda to move toward us, you have to stop thinking about galaxies as solid objects and start seeing them as enormous, fragile structures made mostly of empty space, because the Milky Way itself, the galaxy you are currently inside, is not a dense disk of stars, but a sprawling barred spiral roughly 100,000 light years across, with spiral arms winding outward from a bright central bar, all of it embedded in a vast halo of stars, gas, and dark matter. And somewhere in a quiet outer region about 26,000 light years from the center, the sun drifts along its orbit, completing one slow revolution every 225 million years. A motion so gradual that nothing in your daily life reveals it. Yet you are constantly moving through this rotating structure without ever noticing. The Milky Way contains between 100 and 400 billion stars, a number so large it resists intuition. But the more important fact is how those stars are distributed, because despite the enormous count, the distances between them are staggering, with the nearest star to the Sun, Proxima Centauri, sitting more than 4 light years away, which means that even inside a galaxy packed with hundreds of billions of suns, the average star is isolated in a vast personal volume of space, separated from its neighbors by trillions of kilometers, creating a system that looks dense from afar but is actually incredibly sparse up close. Now consider Andromeda, the galaxy approaching ours, which is similar in structure but larger in almost every respect, stretching roughly 220,000 light years across, containing perhaps 1 trillion stars, with tighter spiral arms and a brighter central bulge, all wrapped inside an even larger halo of dark matter. And despite its immense size, it currently appears tiny in the sky simply because of distance. Yet if your eyes were sensitive enough to see its full extent, it would span several times the width of the full moon, a colossal presence already hanging above us, only dimmed by distance when people hear that these two galaxies are going to collide. The natural instinct is to imagine catastrophic impacts between stars, but that expectation ignores the enormous emptiness between them, because even though galaxies contain hundreds of billions of stars, those stars occupy only a tiny fraction of the total volume, meaning that when two galaxies pass through each other, the probability of any two stars actually hitting is extremely small, almost negligible. And the best way to picture this is to imagine two swarms of insects moving through each other, except each insect is the size of a grain of sand and separated from the next by kilometers of empty space. So when the swarms overlap, they simply interpenetrate, their members sliding past one another without contact, guided only by gravity. This is why galaxy mergers do not produce widespread stellar collisions. Not because the galaxies avoid each other, but because the stars themselves are so far apart that they behave more like individual particles in a vast cloud, passing through and reshuffling rather than crashing. And yet, even without collisions, gravity still plays a dominant role, because every star pulls on every other star. And when two galaxies overlap, billions upon billions of tiny gravitational nudges accumulate, gradually distorting orbits, stretching the spiral arm, and scattering stars into new paths. Gas clouds behave differently. Since they are diffuse and extended, meaning they can compress and heat when galaxies interact, triggering bursts of star formation. But the stars themselves mostly glide past one another, their trajectories bending slightly over millions of years, their original orderly rotation slowly dissolving into a more chaotic arrangement. This contrast between immense scale and extreme emptiness is what makes galaxy collisions so counterintuitive, because from far away they look violent, yet up close they unfold almost silently, with no dramatic impacts, no sudden flashes marking individual encounters, only the slow rearrangement of countless isolated suns drifting through each other like overlapping constellations. What feels like a dense cosmic structure is in reality an enormous, delicate web of motion, where even a trillion stars can pass through another trillion without a single direct strike, leaving the transformation to be driven not by collisions, but by the quiet, cumulative pull of gravity acting across distances so vast that the galaxies appear solid only from afar. The reason this encounter cannot be avoided comes down to gravity acting patiently across immense distances, because although the universe as a whole is expanding and many galaxies are moving away from each other, the Milky Way and Andromeda are close enough and massive enough that their mutual gravitational pull overwhelms that expansion, gradually drawing them together in a slow inward fall that has already been underway for billions of years. And astronomers did not infer this from speculation, but from measuring the motion of Andromeda directly, analyzing the light arriving from its stars and finding that the wavelengths are shifted slightly toward the blue end of the spectrum, a Doppler effect similar to the change in pitch of a siren moving toward you, except applied to light instead of sound. And this blue shift reveals that the galaxy is approaching rather than receding, with a velocity of roughly 110 kilometers per second, a speed that would cross Earth in a few minutes, yet requires billions of years to close intergalactic distances. This measured motion alone already indicates that the two galaxies are on a converging path, but the deeper reason lies in the unseen mass surrounding both systems, because neither the Milky Way nor Andromeda consists only of stars and gas. Each is embedded in an enormous halo of dark matter extending far beyond the visible disk, a diffuse but massive structure that outweighs the luminous components several times over. And although dark matter cannot be seen directly, its gravitational influence shapes the motion of stars and galaxies alike, effectively enlarging the gravitational reach of each galaxy and ensuring that their interaction begins long before the visible parts touch. As these halos overlap, the gravitational field becomes shared, and the galaxies begin to decelerate relative to each other, curving inward instead of drifting apart, their trajectories gradually tightening in a slow fall that resembles two massive clouds drawn together rather than rigid objects colliding. Over millions of years, this mutual attraction grows stronger, not because gravity itself changes, but because distance decreases and gravitational force increases with proximity, meaning the closer the galaxies drift, the faster the inward motion becomes, creating a long approach that accelerates imperceptibly with no sudden moment when the motion begins. Only a continuous pull that has been acting since the early history of the local group. This long approach also explains why the merger does not occur in a single pass, because when the galaxies first overlap, they will still carry enormous momentum, causing them to swing past each other rather than stop, stretching and distorting as they go, then slowing under their shared gravity and falling back together again in a series of oscillations, each pass redistributing energy among billions of stars, gradually draining the orbital motion through a process known as dynamical friction, where gravitational interactions between dense regions and the surrounding stellar population convert ordered motion into random motion, reducing the separation after each pass. Dark matter plays a crucial role in this process as well, because its vast halos interact gravitationally even though the particles themselves pass through one another without collision, meaning the halos merge smoothly while still deepening the combined gravitational well, further binding the system and preventing escape throughout this entire approach. Nothing dramatic announces the change, because the galaxies remain separated by millions of light years. Yet the motion is already determined, the trajectory locked in by mass and distance. And every year the separation shrinks slightly. Every million years the gravitational coupling grows stronger, until the two giant systems are no longer independent islands, but parts of a single evolving structure, slowly tightening under its own weight. What looks static from a human lifetime is in fact a long descent already in progress, guided by gravity alone, quiet, unavoidable, and indifferent to how slowly it unfolds. Long before the galaxies actually overlap, the first real signs of the merger appear as subtle distortions that slowly reshape both systems, because gravity does not wait for contact to begin acting. It stretches objects across distance, pulling more strongly on the near side than the far side. And when two galaxies approach each other, this difference in gravitational pull creates tidal forces that begin to deform their structures, gently at first, almost invisibly, then increasingly obvious as millions of years pass. The outer edges of the Milky Way start to elongate toward Andromeda, while stars on the opposite side lag slightly behind, creating a faint asymmetry that grows with time. And the same thing happens to Andromeda, its spiral arms gradually losing their perfect symmetry as the shared gravitational field pulls unevenly across its disk, producing long, arcing streams of stars that stretch outward into space, known as tidal tails, enormous structures that can extend for hundreds of thousands of light years, made not from collisions, but from stars whose orbits have been gently pulled out of place. These tidal tails do not point directly toward each other, but instead curve into graceful arcs, because each galaxy is rotating while being stretched, so the stars being pulled outward continue moving along their original paths while also responding to the new gravitational tug, creating sweeping structures that wrap around the merging pair like luminous ribbons. From within the Milky Way, these changes would unfold gradually, with Andromeda growing larger and brighter over tens of millions of years, no longer a faint blur, but a dominant feature in the sky, its spiral arms visible as elongated bands of light, while the Milky Way's own band becomes warped and uneven, thickened in some directions, thinned in others. As stars shift into new orbits, gas clouds respond even more dramatically than stars, because they are diffuse and easily compressed. And as the gravitational interaction intensifies, vast regions of gas within both galaxies begin to collapse, triggering bursts of star formation across wide areas, lighting up the sky with clusters of hot blue stars that shine intensely but live briefly, marking the beginning of a starburst phase. These new stars appear scattered across distorted spiral arms and along tidal tails, forming bright knots embedded within glowing clouds of ionized gas, while dark lanes of dust cut through the luminous regions, giving the sky a layered, textured appearance, far more complex than the familiar Milky Way band. Despite the growing spectacle, nothing violent occurs on human timescales, because the distances between stars remain immense. And even as the galaxies distort, individual star systems continue moving quietly through space, their changes measurable only over millions of years. the Sun's orbit, once nearly circular around the galactic center, begins to shift slightly, becoming more elliptical, tilting relative to the galactic plane, the result of accumulated gravitational nudges that gradually alter its trajectory, and similar adjustments ripple throughout the galaxy, with some stars drawn outward into tidal tails, others pulled inward, and many sent into new three-dimensional paths that begin to thicken the disk into a more scattered structure. The overall effect is not destruction, but transformation, a slow unraveling of orderly rotation into something more chaotic. As the spiral pattern that defined both galaxies begins to dissolve, replaced by stretched arms, luminousac, and growing regions of intense star formation, over time the sky would become increasingly unfamiliar, with Andromeda spanning a vast portion of the heavens, tidal streams crossing the background like faint rivers of light, and the Milky Way's once straight band bending and twisting across the darkness, a gradual reshaping driven entirely by gravity, acting unevenly across immense distances. Eventually, the outer regions of the two galaxies begin to overlap, not as a sharp boundary, but as a gradual interpenetration, where stars from the Milky Way drift into regions already occupied by stars from Andromeda. And this moment, often called the first passage, marks the point where the merger stops being a distant distortion and becomes a direct mixing of two enormous stellar systems, with the sky transformed into a layered structure where two galactic cores glow in different directions, while tidal streams and star-forming regions fill the space between them. Despite the scale of the event, individual stars still pass each other at distances measured in light years, meaning there is no widespread chain reaction of collisions, yet the gravitational environment becomes far more complex because every nearby star contributes a small perturbation, and when billions of these perturbations accumulate, orbits that were once stable begin to shift. Circular paths become elongated, stilt, and the orderly rotation of the Milky Way dissolves into a more chaotic motion where stars drift into new trajectories that no longer lie neatly within a flat disk. Gas clouds experience the most dramatic changes since they are diffuse and capable of interacting directly, and as clouds from both galaxies collide, they compress and heat, triggering intense bursts of star formation across enormous regions, producing clusters of massive, short-lived stars that burn bright blue and flood surrounding space with ultraviolet radiation, while shock waves ripple through the interstellar medium, igniting additional pockets of collapse and spreading the starburst across both galaxies. These newly formed stars appear in dense associations embedded within glowing nebulae, and within a few million years, many of them explode as supernovae, injecting energy back into the surrounding gas, further stirring the environment and amplifying the visual chaos. From a planetary perspective, the first passage does not immediately disrupt orbits, because the gravitational bond between a star and its planets remains overwhelmingly stronger than the distant influence of passing stars. Yet the outer regions of planetary systems are far more vulnerable, particularly vast reservoirs of comets like the Oort cloud surrounding the solar system, where icy bodies orbit at distances of up to a light year from their host star and are only weakly bound. As nearby stars pass within a few light years during the merger, their gravity can disturb these distant objects, sending showers of comets toward the inner system over millions of years, increasing the frequency of impacts on planets and potentially reshaping planetary surfaces. This elevated bombardment does not occur as a single catastrophe, but as a prolonged period of heightened activity, with occasional large impacts separated by long intervals, each one capable of altering climates or triggering extinctions if life exists on affected worlds. At the same time, the increased rate of star formation raises the probability of nearby supernova explosions. And although most occur at safe distances, a supernova within a few dozen light years could expose planets to intense radiation, stripping atmospheres or damaging protective layers like ozone, creating additional environmental stress. Meanwhile, stellar orbits throughout the merging galaxies continue to randomize, with some stars flung outward into extended halos, others drawn inward toward dense regions, and many simply scattered into new paths that carry them through unfamiliar neighborhoods of space, altering the long-term architecture of the galaxies. The Sun, if still present, would likely follow one of these altered trajectories, its orbit reshaped but still bound, carrying the solar system through a sky crowded with overlapping stellar populations, bright clusters of newborn stars, and luminous arcs of tidal debris stretching across the darkness, while the underlying motion of everything becomes increasingly irregular as the first passage unfolds over hundreds of millions of years. A quiet intermingling that replaces symmetry with complexity and leaves both galaxies permanently changed. As the merger continues and the two galaxies swing back toward each other after their first passage, the densest regions at their centers begin a far more dramatic approach, because each galaxy carries within its core a supermassive black hole, the Milky Way hosting Sagittarius A times, with a mass of about 4 million suns, while Andromeda contains a far larger black hole, perhaps 100 million times the mass of the Sun, and as the gravitational friction of billions of stars slows the motion of both galactic cores, these enormous objects are drawn inward, gradually spiraling toward a shared center of mass. The environment near the galactic centers is already far denser than the outer disks, with stars separated by light weeks or light days rather than light years. And when the cores pass near one another, the density briefly increases even further, creating a crowded stellar region where close gravitational encounters become more common, altering stellar paths, ejecting some stars at high speeds, and funneling gas toward the centers where it heats and forms luminous accretion flows. Gas falling toward each black hole does not plunge directly inward, but instead forms a rapidly rotating disk of superheated plasma, glowing intensely across multiple wavelengths. And as both cores become active simultaneously, the central regions of the merging galaxies brighten dramatically, not as explosions, but as sustained sources of radiation powered by matter spiraling toward the event horizon. Over time, repeated passages bring the two black holes closer, and once the surrounding stars and gas have absorbed enough orbital energy through dynamical friction, the pair becomes gravitationally bound, forming a binary system in which the two supermassive black holes orbit each other at enormous speeds, separated at first by thousands of light years, then gradually shrinking as energy is carried away. The mechanism for this energy loss shifts as the separation decreases, with gravitational interactions between the binary and nearby stars, slinging those stars outward, extracting orbital energy, and later, when the black holes approach more closely, gravitational waves begin to dominate. Ripples in space-time predicted by Einstein that propagate outward at the speed of light, carrying energy away from the system and tightening the orbit. These waves are extraordinarily weak by the time they reach distant observers, yet the total energy released is immense, because two objects of such mass accelerating around each other generate distortions in space-time far stronger than those produced by stellar mass black holes. And as the orbit decays, The period shortens from millions of years to thousands, then centuries, then eventually to hours, the motion becoming faster and more violent as the final merger approaches. In the last stages, the black holes whirl around each other at a significant fraction of the speed of light, their gravitational fields interacting in a rapidly changing pattern that sends powerful waves through space-time, and when they finally coalesce, the event happens quickly, forming a single larger black hole whose mass is slightly less than the sum of the two originals. The missing mass converted directly into gravitational radiation. This radiation does not appear as visible light. So the merger does not produce a flash in the sky, yet the fabric of space-time itself is shaken. The surrounding region subtly stretched and compressed as the waves pass, an effect detectable only with instruments sensitive to minute distortions. The newly formed black hole may also receive a recoil kick from asymmetries in the emitted waves, sending it drifting through the central region before eventually settling back into the gravitational minimum. And during this period, it may accrete additional gas and stars, further shaping the central structure of the newly forming galaxy. Around this evolving core, the stellar population continues to mix, orbits becoming increasingly randomized as the gravitational influence of the merged black hole dominates the inner region, leaving behind a dense, luminous nucleus embedded within a galaxy whose original spiral structures have largely dissolved. The encounter of the galactic cores does not produce a single explosive moment, but rather a prolonged tightening, a gradual conversion of orbital motion into gravitational waves and random stellar motion, culminating in a quiet but profound transformation at the center of the system, where two separate gravitational anchors become one, reshaping the dynamics of the entire merged galaxy. After several passes through each other, with each encounter redistributing energy and further scrambling stellar orbits, the two galaxies eventually lose enough momentum that they no longer separate again. And what remains is not the Milky Way or Andromeda, but a single merged system, often called Milkomeda, a vast elliptical galaxy formed from the thoroughly mixed stars, gas, and dark matter of both parents, its structure no longer defined by spiral arms or a rotating disk, but by a roughly spheroidal distribution in which stars move along randomized paths, some looping close to the dense central region, while others wander through an extended halo stretching hundreds of thousands of light years into space. The burst of star formation triggered during earlier passages gradually fades as the available gas is consumed or heated and expelled, leaving behind a population dominated by older stars, many reddish and long-lived, with only scattered pockets of new star formation lingering in residual clouds. At the center sits the merged supermassive black hole, now far more massive than either original, acting as the gravitational anchor of the new galaxy, while the rest of the stars orbit within the broader gravitational well, shaped mostly by the combined dark matter halo. From within this new galaxy, the night sky would look profoundly different, lacking the bright band of a disk and instead presenting a more uniform scattering of stars, dense in some directions, sparse in others, depending on location, with no obvious spiral pattern to orient by. Only a diffuse glow toward the central concentration and isolated clusters drifting across the darkness. By the time this transformation completes, Earth itself would already be far removed from any biological significance, because long before the galaxies merged, the sun's steady brightening would have evaporated the oceans and stripped away the conditions necessary for life, leaving the planet dry and hostile. And as the sun approaches the end of its main sequence lifetime, it would expand into a red giant, likely engulfing Mercury and Venus and possibly Earth, or at least scorching it beyond recognition, a fate determined by stellar evolution rather than the galactic collision. If Earth survives physically, it would continue orbiting an aging sun somewhere within the new galaxy, its path determined by the chaotic redistribution of stellar orbits during the merger, perhaps in the outer halo, perhaps closer to the central bulge, but otherwise unaffected by the large-scale transformation, since planetary systems remain tightly bound compared with galactic forces. Some stars are expected to be flung outward entirely during the merger, becoming intergalactic wanderers. And if the sun were among them, the solar system would drift into deep space, leaving the galaxy behind as a distant luminous patch. Though such outcomes remain statistically unlikely compared with remaining bound beyond the immediate merger, the broader local group continues evolving, with smaller satellite galaxies gradually absorbed into the growing Milky, their stars added to the halo, their gas contributing little after the main starburst phase, until most nearby galaxies merge into a single dominant structure. On even longer time scales, the expansion of the universe accelerates the separation between galaxy groups, isolating this merged system from the rest of the cosmos. While internally the galaxy slowly ages, star formation decline. Massive stars, and only long-lived red dwarfs remain shining faintly for trillions of years, over unimaginable spans of time. The luminous population thins, stellar remnants accumulate, and the galaxy positions from an active environment to a quiet collection of fading stars orbiting a dark central mass. What began as two distinct spirals, rich with structure, becomes a smoother Solar System, its past preserved only in the randomized motions of its stars and faint ripples left by the merger. A single galaxy shaped by gravity's long patience and the gradual blending of once separate cosmic islands,